Now we're on live in the coronavirus series. So today we are going to be talking about AVL trees. And this is what assignment 8 is on. And I expect to finish this today. And you will have the assignment, that deadline will stick. But I will still talk about the next class to reinforce it for the test. Especially because we have the spring break in between. So to kind of bring back on the reason why we have AVL trees, let's go ahead and talk about binary. So let's switch back from thinking of binary trees with traversals into binary search trees, which are the ones that if you have a parent node, the stuff here is less or equal, and the stuff here is greater than the parent node, right? So if this is a number like 10, and this is x and y, then x is less than or equal to 10, whereas y is greater than 10. That covers every single case. So that's just a binary search tree. So now, if we are inserting nodes into a tree, how long is that going to take? Well, it depends on the height of the tree, right? If we have a tree like this, in the best case scenario, whether we're inserting, we're searching, or we're deleting something, we have to find it first. And so in the best case scenario, it's going to take at least 3 comparisons. Actually, well, if we're searching, it might take just 1 comparison. We're searching for the root, bam, right? But in the case that we're inserting something, in the worst case scenario, we are going to have to look at potentially this one, this one, this one, this one, and then either this one or this one, right? In a better situation, if we're trying to insert something, in the best case scenario, if we're inserting, we're gonna have to look at this, and then this one or this one, right? That's better because we only have 1, 2, 3 comparisons to look at before maybe inserting anywhere here. Whereas here, we have to do 1, 2, 3, 4, and then 5, whether it's the 5th one is here or here. And then we can insert anywhere here, right? Other actually better scenario where we have to do less than 3, this could be also a good one would be, for example, if we have to insert, what's the color we have in this blue? We check this one, and then we insert here, because we have a spot there, right? So we could actually insert there, and that's only 2 comparisons, right? But the thing is, it can be anywhere from the worst case up here to actually the best case would be here, even better than this one, because it's one less. This is only 1, 2 comparisons, whereas here we had 1, 2, 3. So yeah, this is actually the best one over here. If we mathematically represent that, we can say that the height of the tree is going to be your your big O, right? So you can say O of H. And if you're inserting n elements into that, it's n times h. That's your time complexity to insert all elements into a binary search tree, right? And if you were trying to sort them, once you insert them, you just have to do the in-order traversal, right? That's just an n added to that. So it's irrelevant here because we have an O at the end there, right? So n times h is the time complexity to do these operations on the binary search tree. Now, what is h? H can be 2 things. It could have a situation where the tree is as full as possible. We would say it's a balanced tree, and that is going to be the height is log n of the tree. That's one of the properties that I told you when we were first talking about binary trees. It could also be that h is equal to n. An example of that is a degenerate tree, because that's just basically every single node connected like a linked list. That's the worst case scenario where the height is going to be the same size as the number of nodes, because if they're just like as a linked list, you have to potentially check for example, suppose you were trying to insert something, and the worst case scenario is going to be inserted here or here, which means you have to do 1, 2, 3, and 4, and you have 4 things. So your height is the same size as the number of nodes. So if h is equal to n, then this formula of n times h becomes O(n) squared. But if your height is equal to log n, it becomes n log n. Which one's better or faster? N log n. So because of that, we want to achieve this height. But that's not trivial, because when we start inserting things, odds are that as you insert them, for example, well, if the worst case scenario, if you're inserting something in order, actually, that's going to generate a degenerate tree, right? It'll be 1, 2, 3, 4. The same thing for like descending order. 4, 3, 2, 1. Ideally, something that would be kind of nice would be if we had maybe like a 3, 2, 4, 1. I think that will make a good tree. 3, then 2 goes here, 4 goes there, and 1 goes there. Yeah, I mean, yeah, you can't really do better than that. In fact, this is a complete tree, right? Actually, because every level except the last one is full, and the last level is all the way to the left. But if we have, for example, here a 0, that's not good. Because ideally, in that case, we would have probably wanted to insert the 1 over here. And the 2 there. Because then it would have made 3, 1, 4, 2, 0. And that's much better, right? The height of this is smaller than the height of this. So how can we, without having to manipulate the input, still maintain that log of n height? Well, we do what's called rebalance the tree. Balance the tree is just basically making sure that the height difference between each of the children is less than or equal to 1. So how do we measure that? I might have shown you some other day, but we'll go over it again. We start from the leaf nodes and we work our way up. So this we say has 0 height because there's no children. This has a height of 1 on this side and a height of 0 on this side. And then moving up, this has a height of 2 and a height of 0. This is unbalanced because the height difference is more than 1. Here it's just 1, so that's okay. If we kept going, you would see that as you go up here, this is 0, 0, and then this is 1, and then this is 3. That's also unbalanced because anything that's unbalanced here will kind of cascade into being more unbalanced up there. The one exception to that case is if we had this tree like this. This is actually balanced. This is 0, 0, 1, 0, 2, 0, 0, 1, 0, 2. But if we add another level to this, then this becomes 0, 0, 1, 0, 2, 0. That's unbalanced already there, right? But technically, which this would also be unbalanced, this is technically balanced if you look at that node. So that's the one special case. But usually, if it's unbalanced, that balance will continue upwards. So the moment we find something unbalanced, that's where we're going to take action. So how do we take action? Well, that's the AVL algorithm. So AVL stands for the people that made this, and it's a group of people. Yesterday, they Googled it. It's on the video. It's like, it's an Eastern European name or Polish name or something. It's like Anton Bielik Lampert or something like that. That's what AVL stands for. It's a group of people, I think, or at least 2 of them. And so what they say is this. Because we want to maintain log n height so that the insertions can be quick and we can achieve that n log n speed, what we will do is the moment that something is considered unbalanced, we're going to rotate that piece of the tree in order to decrease the height. So let me give you an example of that first. So let me just create a tree. Let's say we have something like this, 5, 6, 4, 1, and 4. No, that could not happen. 5 could happen though. Yeah, okay. So this is balanced so far, right? By the way, I didn't say this, but I said it before. The way you're measuring this is you have the 0, 0 here. You take the biggest number, and that's the one that you use. So for example, here, suppose that we had a node here that was 8. So this is 0, 0, and then here becomes 0, 1. You take the 1 here, and then bring it up. You don't take the 0, because you take the heaviest side. That's what you're trying to measure. So anyways, this is a balanced tree because no node has a difference of greater than 1. There are some nodes that have a difference that is of 1, which is okay. In fact, we have just one node that is like that. And so ideally, we would want something to be inserted in this spot, but that's not always the case. But it's okay. it'll still be balanced even if we go ahead and add in a couple of more nodes. So suppose that we add in like a 4.5. Is it still balanced? Well, this is 0, 0. This becomes a 1, 0. Then this becomes a 2, 0, or sorry, 2, 1. And then this becomes a 3. That's okay as well. When things are going to get unbalanced is if I try adding something on as a child of this one here. Or if I try adding this one's okay. You can add 2 children on both sides and it'll still be okay with the 1. If I try adding something here, it'll get unbalanced because there's 1 here. So let's go ahead and do that. Say we add in a 9. So the way we would do it is we have a 9 to insert. We look at the root. We see that the 9 is bigger, so we check the 6. We see that the 6 is bigger, so we check the 8. We see that the 8 is bigger, and then we see that it has no children, so we append it on the left side. That's the left. No, that's the right side. Yeah. Okay. So, yeah, because you're looking at it the same way that I'm looking at it, right? Yeah. That's the right side for you. Yeah. Okay. And so we start measuring from what we just inserted up, and always notice something. As when you don't have to recalculate every single node's height. You only have to recalculate starting from that children and up. That the one that you just added. So potentially, I don't want to say half, because half represents like 50%. It's more of like, if you were to cut the tree like this in half, that way of half. If you're only modifying this side of the tree, then that's only the stuff that you're going to recalculate. You may have to do other stuff here if things get unbalanced, but just to calculate the heights, notice that as you're computing these, they don't affect this value. Like this one, the 4 here with the 1 and 2, that height is not modified at all because I'm not touching that side of the tree, right? So you don't need to like comprehensively like recompute the height of every single node. That's a waste of computation, really. So anyways, we insert the 9. So how is that going to change the tree? Well, the height, this is going to become a 1. And then this is going to become a 2. And already there we have a problem. So we don't even go up and check the 5. Already there we're like, okay, that is a difference of more than 1. So you haven't shown the rotations yet, but what do you think I would want to do to fix that? That's our problem area. So that's the only part that we're really going to be modifying. What am I going to do? Well, let me propose the idea of switching the order of those nodes, but still maintaining a binary search property. I can go ahead and sort of imagine that the 8, the 6, and the 9 are being held by a little string. Yes?
How come it's unbalanced now? What's the difference between that 2, 1, 0 and then the one on the left side going from 2, 1 to 0?
Wait, repeat that again?
Your 6, 8, and 9, your subscripts.
Yeah.
You got level 2 for 6.
Yep.
And then 1 for 8 and 0 for 9. But on the left side, on the same levels, you have the same kind of subscript.
I do, but the difference is still not 2. Because look here. The 1 has 0, 0 height, right? Here there's a 1.
Yeah.
Over here we have a 0, 0. Here we have a 1, 0.
Sure.
And this becomes a 2 here. But the difference being that because of this child here, it helps to balance this 4. If there was a child here like a 5.5, then this would become a 1, and then it would be considered balanced.
Oh, I see.
So it really is like you're holding it on a scale. It's not so unbalanced to have a tree of this format. You know, if you think about holding this like on an actual scale, this looks more balanced than that, right? Mm-hmm. Just like physically, if you think of it like little weights. Sure. And so that's why this side is okay, but this side is not okay.
I see.
And mathematically, the way we represent it is we look at the height differences. There is a yes, they both have a height of 2 at this level, but here this is a height of 1 and this is a height of 0. That difference is basically 0 minus 2, absolute value of that.
Oh, I see. So what you're comparing is the 2 different sides of the
Yes.
of the node, not the next level.
Just the heights, that's all I'm comparing.
Yeah, you're on the same level, the 0 and 2 there. Okay, I got you.
Yep.
But when you go up a level, don't you do the height, the max of the previous one plus 1?
Yes.
So then how come it's a 2 on the topmost?
You
It's
didn't
3,
check
2,
that one.
but you didn't do, for the 6, it'd be.
Because I haven't gotten there yet. Before I didn't have the 9. So when I didn't have the 9, this was 0, 0, this was 1, and this was 2, right? I inserted the 9, and I started updating the heights. But then I got to the 6, and I found that it's not balanced. I stopped my height updates, and I balanced the tree before I even check any further. The moment you find a problem, you fix it before you even look at the rest of it. So it's an algorithm that works by locally fixing problems, if you think of it that way. So that's why. So yes, I know that the height really there should be a 3 eventually, but we're not looking at that even now, because we have to balance the subparts. It's another way of thinking about it is you deal with the little problems before they become bigger problems. So it's a bigger problem if the root is unbalanced. So let's fix this, and then if we get there and it's still unbalanced, then we'll deal with that. But first we'll deal with the other problems, the most near problems to us. Okay, so anyway, what I'm gonna do is, again, thinking of this like a scale, instead of holding this string from there, I'm gonna hold it from here. So what I'm gonna do is, I'm gonna pull the 8 up and make that my new root. So I'm pulling it up like that, and that means that the 6 is kind of gonna fall down over here like that. So this is kind of hard to draw, but imagine that I'm holding the 6 here, so it's gonna swing down like that, okay? And then the 9 is still gonna be on the same spot. Okay, so let me make that nicer now. This is okay because that's still binary search, right? It's not violating binary search rules of like less and greater than.
Is there any circumstance where it would?
Where it would? Well, suppose that instead of grabbing it from, well, no, no, as long as you don't change any of the connections per se.
Okay.
Yes, let's think of it that way. Give you an example that I was going to give eventually. I suppose that could be a case where even then it's okay. Oh, wait, no, because this would be a 4. So I guess in this case, if you had something like this, and you try pulling it up, and you're still holding the connections, it would look like that, right? So I guess that would break in that case. We'll talk about that in a second. But I guess I take it back based on that counterexample. Best thing to do is after you try to do something, you look at the numbers, and if they look wrong, then something bad happened. But again, I'm just showing you conceptually what we're going to do. I'm going to show you like a very algorithmic way of doing this.
Okay.
So this is more of I'm trying to get you to understand. It's like I'm trying to make you discover AVL algorithms, like you're just discovering for the first time kind of thing.
So what happens if the 8, it had something on the left side? Because then it would have like 3.
Yes, so that's the other part. These nodes could have children. There could be a child potentially, even though it might actually be balanced if it had the children. Suppose that they had the children anyway. So the possible cases that we might have, and I'll use a different color for them, is we could have a child here. We'll call that child A. You could have a child here called child B, child C, and child D. Child C and D, no problem, they just hang out the same spot they were. Child A also hangs out in the same spot. Child B is the one that is actually going to get readopted by somebody else, I suppose. That one is going to be transferred over here. And that's okay because the position that it's at here, in this one, on this one right here, it says that child B, and here I can write it, child B is greater than 6, but less than 8. That is the rule of child B because it's in that spot. This also holds here. It's greater than 6 because it's on this side, but because it's on this side from the 8, it's also less than 8. So in both spots, it holds true. And again, algorithmically, that'll always be the case. That's actually going to be a little thing that I'm going to show you. But yes, that's a very good thing that you're already thinking about. Yes, we have to think about the children, as I tell people. Think about the children. So, what's that?
The younglings.
Yeah, think about the younglings. Anakin thought about the younglings. All right. So Yeah. So eventually you can see that, yes, we will have to deal with these children. But for now, let's go back to just doing this rotation that we did. So we did the 6, the 8, and the 9 that rotated like that. So now that once we've rotated, we can go ahead and replace what's in that square with the newly performed rotation. I'll go ahead and, so I don't write it in case you want to have it in the notes, I'll do it down here. So what we're going to do is we're going to replace this with what we just rotated, which was this. And we still have that link. So that right link that was coming like that, we still have that. That's important that we keep that the same way. So once we perform a rotation, what we're going to do is we're going to go ahead and see if we're good now, if this fixed it. So we can recalculate the height of everything that we just rotated, and all the children as well. So we start at 0, 0. We go ahead and we say 1 there. Over here is also 1. We take the biggest of that, which is 1. And then now we can go ahead and move up the tree and see if we got to fix anything above. In this case, we go ahead and recompute this. That's also just going to remain as 2. And at that point, because we got to the root and the root is also okay, that's when we can say the tree is still balanced. We don't need to check anything on this side because of what I was saying. We were basically just messing around with this side. Therefore, nothing needs to be checked over here as long as the root says it's okay. So that's pretty much the end of that. How do you feel about that though? Okay, so now, this is cool, and hopefully you kind of got a feel for how to do this conceptually, even if you didn't know the algorithm. But of course, people already thought about this, and they came up with the following rules. There are 4 rotations that an AVL tree can do, and yet again, I don't memorize all of them. I only know one of them, and that's because, as you will see, you can derive the other rotations from the first one very easily. You either are mirroring them or doing them on the children's. So the first rotation that we actually have already seen, that's convenient because that was on the same side too, is actually what's called as a left rotation. That's what we just performed. We performed a left rotation where we have the values x, y, and z, and those values are going to get rotated from this format into this format. As you can see, the numbers 1, 2, 3, and 4 just represent the location of the nodes. They don't necessarily mean that they're in that order, although in this specific one they are, but I think in one of them they're not. Yeah, this one I put them backwards. I guess if I want to be consistent, and some people kind of got OCD about that, I can go ahead and do that. That way people don't get triggered. There we go. Okay, so now they're all the same. So now I think they all, even if they were to actually represent real numbers, then they would still be, they'd still be like in binary search property. But I don't want you to think as numbers. I just want you to think as variables. The only reason I didn't use other letters was because I wanted to signify that those are children. But the real rotation is happening on the letters here, the x, y, and z. So when you have something of this form where you have x, y, z, and as you can see, the unbalance, and that's what I have this really tiny picture for here, the unbalance is happening on the right side. So the right side is heavy. We have a right side heavy tree, and I know this is kind of strange, but on the right side heavy tree, you perform a left rotation. The opposite of that is basically the mirror of that. So you've all been coding mirror function for assignment 6. So that's essentially what the right rotation is. The right rotation is just the mirror of that. If you have something of a left heavy tree, you perform a right rotation. And it's the same concept, just the mirrored version. Can you see how they're basically the same thing? You have instead of having x, y, z, you have z, y, x, or you can also think of it as x, y, z if you're looking at it from here. But eventually all you're gonna do is, you're going to just take the y still and make that the root, and then move the children, and only one children needs to be moved, basically. That's the child of y is going to be moved to the child of z. And it'll still hold the property that I was saying, where the child of y, so 3, has to be greater than y but less than z, which holds for both sides of that. On the left side it holds, and on the right side it also holds. It's just a different spot. Now, as you can see, do you really need to memorize both rotations? Not really. You can just, I mean, if you really have a hard time, if you're wearing like a watch, you can use it as a mirror and see it backwards, but you could probably, as long as you remember one of them, you can do the other one. And you can probably even not have to memorize it. It makes sense a little bit, at least after you use it. The tricky ones are the next two. But before I show them to you, we're going to also try to kind of derive them. So let's go ahead and just try to use at least the first 2 rotations until we basically can't use them anymore. You'll see something that could happen. So I was using letters last class. I can use letters again, or I can use numbers. Preferences?
Doesn't matter.
Letters again. I used Corona as an example last time. So how about we use, what? Ebola. Let's use Ebola then. So we're going to insert Ebola into a binary search tree.
What about Zika? Z-I-K-A?
That's too short.
Okay.
In fact, we might have to do Ebola virus. Okay. So let's go ahead and do this. Let's insert this into a binary search tree. So when we don't have anything, we go ahead and we just create a root. Next, the B is going to go on the left side. Then after we insert something, what we're going to do is we're going to recompute the heights. So that's okay. We're still good. All right, let's insert the O. You guys double check that I don't insert in the wrong spot, because it's possible. So now we got the O. We go ahead and recompute the heights technically of this side only. So 0, 0, and then this one becomes a 1. We don't need to touch the B and the E's heights. We just got to make sure that this is okay. And it's still okay. All right, let's do the L now. L should go right here. So we check here, put there. And then that's a height of 0. So then this is going to get updated to a height of 1. And then we take the bigger number of that, which is 1. And then this becomes a 2. And everything's okay because the difference is less than or equal to 1, right? Here, I'll put that somewhere here. As long as absolute value of the difference is less than or equal to 1, we're okay. All right, so let's insert the A now. A goes here. This becomes a 1. This becomes a 2. We're still okay. As we said, that's why we needed a longer word. We got the V now. So the virus is coming in, and where's the V gonna be inserted in? Over here, right? So this is 0, 0. This gets updated to a 1, and then this technically is still 2, because 1 is still bigger. So I. Where's I gonna go? Here, right? Make it so it's easier to not get confused with the L. Okay, so that's 0, 0. 1 there, 2 there, 3 there. It's still okay. The R now, where's the R gonna go? O, V, R, right? 1, 2, and it's still balanced. U. Okay. 1 there, and 2 there. Yay! Finally, I thought we wouldn't get anywhere here. So we got an unbalance right here. We do not even recompute anything up. At that point we're like, we need to fix things now, right? I like this too because this is what I was trying to get to. So, which rotation do you perform? Well, which side is heavy?
Right side, so left rotation.
Which side? Are you sure about that?
Left.
Left side. Okay. So you do a right rotation.
Yeah.
Right? Right. Okay. So, are you really confused? So, it's backwards. So because this is left heavy, rotate right, I suppose to boost the right side. You can think of it that way. Rotate right to boost the right. Okay? It's like if you got a majority on the left side and you go and vote for the right or something. I don't know. So, okay. So then you're like, okay, well, let's go ahead and do that. Which one's the right rotation? Well, that is this one. So as you can see here, I do it really tiny. At least I did it on this one with the little dots. I didn't do it for the rest of them because that it required a lot of art. Oh, I see. What I did is I was zoomed in. No, that doesn't work. There we go. So you have something like that, and then you have 2 0 1 0 0 0. Okay. So hopefully that helps you to remember. Okay. So that's when you do your right rotation, because you have the left side heavy. Okay. So this is, in fact, for now, since this is the first time we're doing this, let's go ahead and copy this down. Actually, because I'm lazy, we're going to copy both of them then. There's a little foreshadowing happening here. Still kind of readable, right? At least, I mean, the child are a little bit hard to read, but we can zoom in. So here's the thing. Okay, let's try that. So first of all, we have a little problem here. Their algorithm for the right rotation requires 3 letters, but we only have 2 of them, right? So what do I do? Okay, if you run into such a situation, you can go ahead and generate a temporary, like, imaginary node, and you can call that A. And as long as you have that imaginary node, now your algorithm works. Yay. You can also think of having temporary children for any of these nodes. So now we can have, numerically, that was 1, 2, 3, 4. So here's our 1, here's our 2, here's our 4, and technically the U is a 3. And then if you really just, so you don't want to get lost, you can also consider this to be X, Y, Z. So this is X, this is Y, and this is Z. Okay? So now we can basically just do exactly what this says, which is make the R the root, keep the A over here, put the V down here, the A's children remain the same, V's 4 children is here, and then U, which gets moved around from the Y to the Z, gets essentially put there. Let's make it bigger. In fact, let's make it like that so it's easy to we don't get it mixed up. And there you go. After you perform the rotation, you can go ahead and delete all the temporary stuff. So delete that, and then delete the 4. And then you're like, well, I guess I'm done, right? So let's go ahead and figure out and see what happened.
Just forget about the S.
Oh, that's resurgent. RVU. RVU. So you recompute your heights, and then you get here, and you're like, that didn't do anything for us. It just flipped the program around, right? From there, you basically got like a backwards of that, but it didn't fix it. So you're like, oh crap, what do I do? Well, why don't we do another rotation, right? See if it fixes this time, It's like if the code doesn't compile, and you're like, maybe if I compile it again, it'll be fixed. I've seen that happen. That's when you don't link your libraries correctly. and then the first time they build the libraries, and the second time it recompiles, but it looks for the libraries which you just built, and then it compiles, and that's you're like, whoa, black magic? It's not black magic. It's just bad order of your compilation of your makefile.
That happened to me during Inception. I literally like compiled the sec files and recompiled and it all worked correctly.
Yeah, that's the solar flare touches the computer, as Ed says. So, anyways, let's go ahead and do that. So that's why it kind of foreshadowed that now we're going to be using a left rotation. So same thing. We're going to throw in an A. This time I'm not going to do all the magical colors. And then this has no children here. Over here, though, we do have the child that got moved from you. So that's that one. And then these have no children, technically. So after we remove that temporary, we end up with this, which essentially is what we started with. You see that? VRU, VRU. So we end up where we started. And yet again, of course, when we compute the heights, we still have the same problem. That's when you start sweating in the midterm. Like, I don't know what am I to do. So, what can you do here? Stack Overflow.
Throw it away.
Throw it away? What does that mean? Throw your grade away?
Yeah. Close enough.
What you would do in this case is you think outside the box.
No, you just erase the box.
So,
Exactly, erase the box.
you raise the. Actually, I don't have to raise the box. But what you do is, you're like, okay, the problem is this has some weird shape that's like a thing. It's like a Pac-Man. So, what you're gonna do is, instead of rotating the node that's broken, try rotating the child and the grandchild. This is the one time that I use that grandchild terminology. Try rotating that. So instead of having VRU, let's go ahead and rotate the R and the U from this to this. Gosh. Wait, was that an RU there? Oh yeah, I don't remember my alphabet. I was like, that doesn't look right. But no, that doesn't look right. That is, that's good alphabetically. Okay. Interesting. I don't know. That looks weird with the R and the U there. I feel like U goes first, but okay. Anyways, so yeah. So you try doing that little rotation there. Just switch the technically the child and the grandchild of the problem node. You flip them around. So now the kid is the dad and the dad is the kid, basically. And so now, what is this going to look like? It's going to look like this. Agreed? Okay. That's a simple rotation that we can do. Now we can just go ahead and do the right rotation again. This one. Oh. And then go ahead and flip it like this. And then put it back into our little spot. I don't know. Sometimes it's just a lot of copy pasting, and I do like the fact that we can have the online stuff. But see, then this happens.
But you can't do any of this with the whiteboard.
Yeah, but you can do it faster. I don't know. Anyways, so you perform that rotation, and now if we recompute the heights, yay, we're good. And now we move up, and this is good, and then this is good, and then we're good to go.
I have a question. Instead of performing that little rotation, could you move that, because you have that little sign, Pac-Man sign thing?
Yeah.
Could you just take the bottom node and move that up to the, where the, like say the U and V just switch those, and take the V and just push off and make it a child instead of doing a rotation?
Yep, that's basically what the algorithm says to do. So those, what you said, is exactly what the left, right, and right, left rotation are. That looks light, but it's an R. There you go.
So can we just check for that first, rather than do the other two and then get back to the starting point and then do that?
So here's the issue with that. It's very hard to check for that because in this case that you saw, usually when you're inserting, you don't run into this. But when you're deleting nodes, it's ambiguous. Last class, when we did, I think it was the word Corona, or I don't know which one it was, it gets to a point, for example, here, that you insert more childs, and so at some point you see that this becomes like, for example, suppose that I went ahead and deleted like, it's hard to come up with an example for that, but in fact, why not just look at the other classes example? I think it was this one. No. Which example was it? Oh, I don't remember. Well, here, let me just come up with an example. So let me go ahead and modify this. Let me copy and paste it so we back it up. The problem is when you have children around, it's not as easy to see which rotation you have to do. And that's kind of what I want to show you. So suppose that here we added another node, let's say W. So this becomes 0, 0. This becomes a 1. This becomes a 2. This becomes a 3. And then, okay, this will work. This becomes a 4. Okay, so we inserted that W and now it becomes a 4, right? We have to perform a rotation here. It's very possible that the rotation that we have to do is just that, but it's also possible that the rotation we have to do is that. That's when it becomes ambiguous on which one you have to do. And you're not going to know. So the best way to approach that is to try to perform a simple rotation first. If it doesn't fix it, try to perform a simple rotation again, because that'll bring you back to the original example, and then try to perform a double rotation. Because at this point, in fact, let's try it. Let's try it on that one. Because I mean, so far we're good, right? So instead of inserting what was the last letter that we had to insert? The S of virus?
Yeah.
Yeah.
That's perfect. Oh no, because where's it going to go? R? Okay, so that's perfect, yeah.
To the right.
That's what I meant. Okay, so that's great, because I think we're gonna have the same situation. So see, Ebola virus is a great example.
Like it's meant to be.
Yeah, it was meant to be.
What do you do with
Just
duplicates?
as nature intended.
With duplicates, you insert them on the left side and then on the rightmost spot. So like if you have a E and then you're inserting another E, you insert it here. And then you have another E, then you would actually insert it here. And so on. And you keep doing that.
The leftmost spot?
Hmm?
The leftmost spot.
Well, suppose that then you had like a V, well, no, that makes no sense. An A here. Where would E go? The next E, if you had another E.
To the right, right?
To the right of A. So left, but rightmost as well. That way, when you do the traversal, the end of the traversal, it'll maintain its spot. Okay? So, anyways. So we got 0, 0. So here we have 0, 1. Then we have 2, 1. Then 3, 2. And then 4, 2. So we got to do the rotation, right? Okay. And I mean, that looks scary. So we will try to do the simple rotation first and see if that's okay. So we will try to do the X, Y, Z rotation where we have 1, 2, 3, and 4 for the children. that means, and I'll do it up here so I can see, O is going to become the new root of the tree. Well, here, I don't know if you want me to show this one too, but I'll put it for my own benefit as well. 1, 2, 3, and 4. That's a Z, I guess. I'll put that to make it different from the 2. Okay, so that means that the O is going to become the new root. E is going to come down here. U is going to remain there. And then children-wise, B is going to still be over here, which means anything after B will remain the same, so that's A. Over here, to the right of the E, is going to be the L, right? Because the L, this one over here, it would be the L here. So that's the L. And the way you can check after you do a rotation that you didn't mess up like in a test is like make sure that it's still in binary search style. Okay, and then you should have everything the same, which is bad, right? Perfect. Yeah. Because it's still messed up, right? Yeah? It's still messed up, right? Well, we'll recompute it. Let's recompute it. Oh, well, the I should remain in the same spot. Because any generations after this, so any guy coming out of there, all those are still the same. So yes. Which is great because when you're coding this, you don't have to worry about messing with those pointers. They just move along with the thing. So this is a great example where I think, actually, well, we'll see. Let's figure out the heights of the whole thing. Since everything got messed around and moved, technically, this height is still the same with the L, so this is still 1, 0 here. And then this is also 1, 0 here. You don't have to recompute those. And same with anything less under the 2, or under the U, should also still be the same. You don't need to recompute those either. But from there, you got to recompute. So let's go ahead and try to recompute. So this becomes a 2 here and a 1. Oh, sorry, a 2. Yep. And, oh, so they get fixed. We're good. So that's a case where, like, it could have also been that we could have tried to rotate this one instead. You know, but it wasn't biggest. And there's going to be cases where this would have been the right rotation to do. No. Yeah, that was interesting.
It would still keep the binary search format.
All of the rotations should always maintain binary search format, yes. And they will maintain it. But I'm just saying that rotation may have been what we needed to balance it. I can try to show you where that is the case. If we didn't have the I, maybe that would have happened, I think.
Could we try doing it that other way that you just highlighted to see what would happen in case it would be like that thing where we'd have to do a double rotation?
Sure. That means that we would have rotated. So here, let's take this one because this is the nicely drawn one. And let's add the S to that. We basically will just have to do the examples for the rest of class. So that's all we have for topic. So we added that, and then one, 2, 3, and 4. Okay, so now that we have this nicely done, let's go ahead and paste it down here. Okay, so let's back up. Let's go ahead and perform the rotations that you're saying. So we want to do this one instead. That one requires us to do a soft rotation on that tree first to basically flip the O and the L so that they become that way. Agreed? That's what that rotation is doing. So that means that this is going to become L, O, and then the children will be dragged along. So I is going to be there, and then that is all going to be the same after that. So that's the R, the V, and the S. And the only one that gets moved around is the R, or actually no, oh, nothing, because L doesn't have a child, so that just stays like that. So if you were to perform that rotation, well, let's figure out what the heights are now. The height doesn't change from the U, so that still remains that way. So we only need to go from there. And so now this becomes 3, 0 there. And then that's nasty, because like the problem has gone even lower now. So then you could try maybe rotating that. So let's go ahead and do that. Let's try to rotate that and see if we can fix this from another way. So I feel like we have more letters than we had before. No. Oh well, yeah, but that's because that's just this here. That's just still the same. But I was thinking in the subtree we might have more. But okay, so in that case, let's try to perform a rotation on the part that's messed up, which is here. So bring up the U, V, and then the S is in the same spot, and then the R gets moved around into here. And now it's good, at least that much is good. So then you go ahead and continue where that was, where we had this. That's not, I mean, it's neither, my bad. Let me move this so we have space. So I can feel the loss and like you guys just got lost there.
The trees all blend together.
Make a tree.
Let's draw the tree again. So it's nicer looking. The user struggle. Okay, there we go. So this is 2, 2, 3, 1 problem there. Yeah? I think did we end up with what we started with now? Is this the one that we started with? I think it was. Where is it? It should be, I copied it somewhere.
It's definitely going up.
The problem is, it's going up slowly. Let's keep going. Maybe it'll get fixed. You can see though that having done the other rotation, we fixed it with one single rotation.
Right.
Here we're just like hoping for the best at this point.
Did it matter that S was in the wrong spot?
Yeah.
Oh,
S is in the wrong spot.
when did that happen?
You think
When you
changed
first wrote it?
Oh,
Oh, it isn't, yeah, sure is.
no, it doesn't quite matter as much. You know,
Still, it's been in the wrong spot for a while.
like here, it would have been over here.
You're still gonna get the 3, 0,
Yeah.
right?
Yeah, and up here, these just get flipped around. So now this is, instead of 1, 2, it's 2, 1. But everything else is the same.
Overall, still a problem. Just
See? So everything is actually still the exact same. It's just that one tiny change.
Actually, that becomes.
This one's okay. This one here, for example, instead of being 0, 1, it's just 1, 0. Oh, well that one, ooh.
No, you move it over to the R. 'Cause it's supposed
Okay,
to
so
be-
here it changes something. Yeah, so it's over here.
So you get 3, 2 on the U.
So then here we have a 1, 2, 0, so bad problem there. So we can fix that with a single rotation though, right? That just becomes, whoa, oh, this thing looked like it turned off. Okay, that rotation is there. And then it's still 2, 2 there, and it's still 3, 1 here. So ultimately, we still have the same 3, 1 here. It's just things got moved around, and now it's in this format. This one, so then I'll clean it up for you guys. So here we have the R is now here. O, S. Like that. But yet, the problem is still the same. We still have this guy here. So ultimately, it changed not much. Okay, so which rotation do we do there? Again, it's ambiguous, isn't it? Pick one. Well, if you want to do it the smart way, you do the simple rotation first. If it doesn't fix it, you redo the same rotation to get back to the original one, and then you pick the double rotation. So let's go with the smart way of doing that. So the single rotation says, actually, is there even a single rotation here? It would actually be, it's right heavy, so let's do a left rotation, right? And left rotation is that forward diagonal. So that's left rotation is like that. So that means we're going to be rotating it on these three. Okay? So the new tree is going to have an E, a B, and an A. Here, let me copy it one more time, like that. And then let me put these down here so I can zoom in a little bit. Okay. So we're rotating this now. So that means that the U is going to become the parent, and L and B are going to be like that. But let's do it actually down here so we have space to put the children. Where are the children going to go? Well, if you remember the algorithm, X, Y, Z, it's 1, 2, 3, 4, and then it becomes X, Y, Z, and then the children are 1, 2, 3, 4. That means that the I is going to move over here, so it's going to stay in the same spot. It's only one child moves, the other three should stay in the same spot. So the children of V stay in the same spot, which are none of them, so that solves that issue. And then the only one that gets moved around is going to be child of R. So basically this subtree, the entire subtree, is going to be moved around and be placed here. Okay? Because a child, we consider that the child, and obviously everything we needed. Okay, what did that do to us here? We're still uneven. So that is a sign that we have to do a double rotation, basically. So to fix it, let's go ahead and do the other rotation again, which will bring it back to the original one, because odds are that in your code you didn't have a backup of it, because it's just too much work to do a backup of it. So let's just go ahead and perform now. It's left heavy, and now we perform a right rotation.
Would it be smart to create like a 10 line rotations?
I think that's more work than just more coding work, because you have to code a way of backing it up or something. I mean, actually, no, you already have a copy function, right? So either, you could do one or the other. Doesn't matter. You could either use that copy function to back it up and undo it, or just do a rotation, which will undo it for you automatically. As long as you do the rotation on the right spots, of course, which is the same one, just back the other one. So in this case, the same nodes technically. All right, so then that becomes an L there. And then we have the I and the U. And then we got to move the children around. So I has nothing to be moved around. U still has the V child. And then the R stuff is going to move from being at the L to being over here. And we should have ended up with the same thing. So let's see. Is that what we started with? I think so, right? This is the one that we started with. Yep, looks the same. See that? I'll zoom out so you can see them. See, they look identical. So see how the rotation brought us back from here to here? And they're the same. So we're back to where we started. That's okay. That's actually kind of what we wanted. And so now we can go ahead and perform. Instead of doing, we can recompute the weights just to make sure. We have a 2 there and a 1 there and 3 and 1. And so instead of performing now a right rotation, or sorry, a left rotation, we're going to perform a double rotation. And that means, because really the problem we have here is this. We have the Batman thing, as somebody called it. So we're going to rotate to straighten that like that. So this is going to go like that. Okay? So how do we do that? Quite simple. Do the rotation on this one. And before we needed that imaginary A, but here we don't need no imaginary A's. We got to know. We'll actually use. So we'll do the rotation on that. We're doing the green rotation, okay? Green rotation basically says make that the root. Well, here, I'll put it if you want to see it. X, Y, Z like that. And all I'm doing is this, by the way. A left-right rotation. So I could go straight from this one here to this one, as somebody was saying. But I'm gonna go show you each step. But ideally, you can either code that, or even when you're coding it, instead of coding 4 functions, you could just code 2 of them, left and right rotation, and then you just call the 2 functions inside of your left-right function, you know, and save time. Or you can just hard code the move as well into one function of its own. You know, however you want to do it. But anyways, so we're gonna perform that rotation. So that's gonna make O, R, U. And then the children are going to be, O has no children. And then U does have a child, so that stays the same. And then the S gets moved around. The S is just all over the place, but yeah. Okay, so then verify what's up here. 1, 0, 2, 1, that's all good. And then of course this came from that one, so this is part of the IL, which is coming off of here. And it's okay, don't panic because it's still unbalanced because it's a double rotation. We only have done the first half. We gotta do the second half. Now that we did that, then we can perform the rotation on this. That's the second part. That's going from, we just did this one here. And now we're gonna do that one. Or actually, we did this one, right? Yeah, we did this one, right? We did right, left, and now we're gonna do left, right. There we go, because it was like this, and we made it like that. Yeah, and now we're gonna go from this to that. Okay, so it's a right, left. Okay, so then that means that R becomes the new root, and then we have the L and the U. And then we just gotta make sure the children get put in the right spots. So I is still gonna see how this own, L has the same children on the left, and U and S, and V and S are still here. The only one that gets moved around is the O. From here, it's going to move here. As you can see, this looks really beautiful. It's like a complete tree, right? Right there, it's a perfect tree actually. Or at least the subtree is. It's perfectly balanced as all things should be. And then, so what was it on top of that? This whole thing came from somewhere, right?
Somewhere.
Oh, EVA, that's right, EVA. So this came from an EBA. So that's 0, 0, 1, 0, 2, 3. Would you look at that? We just finished. In time too, because we got 5 minutes. Which I will open the floor to questions. All of that to insert Evola virus.
So basically, we should have just started off with a simple rotation first. That was a lot of work for the other one.
Yes, we should have started with a simple rotation. Because look at that, that's right, we did that, and it was okay, right?
Yeah, first time.
First try.
Yeah. So always go with that logic of do a simple rotation. Do simple rotation. If it fails, you do simple rotation again. Which is the opposite.
How hard do you dig yourself into a hole?
And that brings you back to the original one. Then perform a double rotation.
get enough, do you always end up, you know, with like a?
With balance?
Balanced tree?
Yes, yeah.
Okay.
Is there a real purpose to have a balanced tree?
Is there a real purpose?
Yeah, like.
Well, yeah, of course. If a balanced tree means the height is log n. If the height is log n, it means it takes log n time to insert things. So we went from an algorithm that could potentially take O n squared to an algorithm that takes n log n. That's faster and better. So if you're performing a sort, doing the in-order traversal of this tree will give you the sorted list. Let's do that real fast. A, B, E, I, L, O, R, S, U, V. A, B, I, O, L. Yep, that looks sorted. Inserting that took n log n time. Doing the order traversal just took n time, so it's just a plus n. So technically n log n plus n.
Do you mind scrolling up to your double rotate algorithm so I can copy them down?
Like the big one?
Yeah, where you have it written down, those ones there.
Yeah. And it's on the PDF too. So I just tell her. So yeah, it's useful. It's actually useful for us.
Do you need an office next week?
What?
Do you need an office next week?
Yes, I will be there. I have, and well, here, let me stop the recording, but I'll be there. Yes. All right. Thank you for watching. Stay safe.